Greetings of the season from Total Output Power Solutions. In our last chapter, in our last video, we talked about the condensers and some points about the condensers. In this video, we will be talking about the performance of condensers in thermal power plants. I am Manohar Tatvavadi from Balewadi, Pune. Well, the condenser performance is just we guess it by the condenser back pressure deviation from the design, which will indicate the performance deviation. Now the condensers are designed for certain parameters which may vary, such as cooling water inlet temperature because of atmospheric changes, then flow maybe because of the pumps, and ambient temperature also because of the atmosphere changes, and the inlet steam parameters maybe because of load. So hence we carry out the calculations for the expected back pressure first and then calculate the deviations from the same to arrive at the variations due to CW inlet temperature, variation due to CW flow, and variation due to dirty tubes. So these three things we'll be finding out today. The now we first discuss about the condenser design parameters. So a sample case I have taken is the condenser back pressure is 78.50 mm of Hg absolute. Cooling water inlet temperature is 33 degrees centigrade. Cooling water outlet temperature, the condenser has been designed for 42 degrees centigrade as the outlet temperature of cooling water. Cooling water pressure drop across the condenser is 0.34 kg per square centimeter. Cooling water flow is 34,500 meter cube per hour. Condensate temperature is 46.70 degrees centigrade. Number of tubes in the condenser are 15,664. The length, OD, and the thickness of the tube is also given. Now the parameters, if I make an Excel chart or maybe a chart there, spreadsheet, I can have the parameters, unit, design value, and the test value. It's a 210 megawatt unit where the condenser pressure, the test value is different and the design value is different and the test value is different when we are actually testing the condenser. So the condenser pressure in the test value is 120.8 millimeters of Hg absolute. CW inlet temperature, you see it was designed for 33, but the temperature was 34.16. CW outlet temperature 45.09 in the test this thing. So the pressure drop, it has not been measured, but it can be measured. Cooling water flow, it was designed for 34,500, but the flow is now 30,000. Condensate temperature, this temperature is 55.56. The air suction temperature was also measured. There were two condensers, so A and B, and the total number of tubes, now it was 15,664 and it is now 15,000 only. The tube OD and these, they have been given. So these are the parameters, we take it down. Now the tapping arrangement for the measurement of back pressure. We measure the back pressure of the condenser. So the tapping will be done like this. You can see the impulse line from condenser, they go to the top operating floor, and where there are two absolute pressure transmitters, we will give you the absolute back pressure in the condenser. Then you can see that the slope of the impulse line to be kept towards the condenser. It must be kept towards the condenser so that you can get the accurate thing. So this is the tapping arrangement for measurement of condenser back pressure. Then the CW inlet and outlet temperature measurement. For this purpose, you can see in the figure the condenser is there, then CW inlet and CW outlet is there. So in the inlet part, you have one thermowell for RTD on the CW inlet pipe, and there are 4 thermowells on the CW outlet pipe, which have to be measured very carefully. So 4 number of thermowells to be provided on each CW outline at a convenient place above the 0 meter level for CW outlet temperature. Now 1 number of thermowell is to be provided on each CW inlet line for CW inlet temperature. Then all thermowells, they are to be approximately 300 mm of depth so that the temperatures can be measured accurately. The condenser hot well and air suction temperatures, they are measured like this. The condenser hot well temperature is measured from just below the hot well. You can measure the hot well temperature, condenser temperature, and which can be taken from RTD or thermocouple provided to the hot well and CEP suction pipe nearer to the hot well. Air suction temperature is to be taken from the air suction pipes going to condenser from ejector nearer to the condenser. So before the condenser wall, before the air extraction walls, the air suction temperatures can be measured. Then the cooling water flow. Now this cooling water flow is measured by portable ultrasonic flow meter. So this portable ultrasonic flow meter can measure the flow through the pipes of the CW pump. So CW pump discharge pipe, you will have to fix two sensors. I think the difference would be around 1 meter. So it is there around minimum 1 meter length within a straight pipe of around minimum 2 to 3 meters straight length with full discharge. The pipeline should be full of discharge. That is, so it can be measured by an ultrasonic portable flow meter. Then we move towards the calculations. Now the pretext is saturated steam temperature. The exhaust steam is to be condensed by removing the latent heat of the steam. So the saturated steam temperature refers to the saturation temperature of the exhaust steam and is as per the steam tables at the LPT exhaust steam pressure. Then there is expected design condenser back pressure. This is derived first from the design back pressure after applying the corrections, because it may change for a varying load, varying CW temperature and CW flow. So it will have to be corrected for that. The expected design condenser design back pressure. Then water velocity in the condenser tubes. First of all, we calculate the water velocity in the condenser tube, the design velocity and the actual test velocity. In the test, what is the velocity? The formula is given there: CW flow rate into 10 to the power 6 tube velocity into 3600 into tube area, number of tubes minus tubes plugged. So in the design, no tube plugging is there, so we calculate it for the whole water velocity in the condenser tube design. It comes to 1.05708 meters per second. And when the tubes are plugged, around 664 numbers of tubes are plugged, so the water velocity in that case comes out, and the flow has also reduced, so water velocity in that case comes out to be 1.05588 meters per second. Then we calculate the condenser duty, which is equal to CW flow into Cp into T out minus T in into D. So the abbreviation Cp is the specific heat, C is the specific heat of water, that is 1 kilocalorie per kg per degree centigrade. Then D is equal to 1000 kg per meter cube, that is density of water. So the design heat load, and you can calculate the test heat load also. So you will see both the calculations have been done, the design and the test condition heat load. Now one more parameter is there, which is log mean temperature difference. So the computation of log mean temperature difference, it can be calculated by the formula that is given there. And so you can calculate the LMTD design, because you know the design parameters, and you can calculate the LMTD test also. So log mean temperature difference for test, as you can see the calculations have been done, and it comes out to be around 15.28 degrees centigrade, whereas the log mean temperature difference in the design, it comes out to be as 9.28 degrees centigrade. Now that was the test and the design, but the LMTD expected, because of the correction of CW inlet temperature, then correction for so first of all we get the correction for CW inlet temperature, which is equal to this formula is given there, So it comes out to be Ft comes out to be 1.013177. Then correction for cooling water flow. The cooling water flow is also less, so we calculate the correction for that also. Fw, that comes out to be uh, because the 664 tubes have been plugged, so it comes out to be 1.05708 meters per second. That is the design, and the test is there calculated. So the Fw comes out to be 0.99943. Then correction for heat load. The load is also, heat load is also there, which is also different from the design and test. So that comes out because of the varying flow. That comes out to be, Fq comes out to be around 0.86085. So the LMTD expected will be equal to LMTD test into Ft into Fw into Fq, and the LMTD expected comes out to be 13.32 degrees centigrade. This was the expected LMTD. Then now we have calculated these parameters, but we have to calculate the breakup of the variations because of the, maybe the flow, because of the condenser tubes blocked, or because of the dirty tubes. So this we have to calculate. So we go for that, and here the calculations of expected condenser. First of all, we calculate the expected condenser back pressure. So this will be equal to the we calculate the saturation temperature expected. It is given by the formula there. Here E raised to Z is calculated, and first of all E raised to Z is calculated, which is equal to the Z also has been said. Actually, E raised to Z is 2.71 raised to Z. Z is a constant, and that constant has been calculated as 0.67528. So the saturation temperature expected, you can see it was expected that the saturation temperature would have been 51.3302 degrees centigrade. So the expected back pressure would have been the it is derived from the steam table corresponding to this saturation temperature, which comes out to be 98.934 mm of Hg absolute. Then now we calculate the back pressure due to Cw inlet temperature and back pressure due to Cw flow. The back pressure due to Cw inlet temperature would be equal to the Cw inlet temperature plus the temperature rise plus the design TTD, which would come out to be around 46.7 degrees centigrade. So back pressure for this calculated from the steam tables for 46.7 degrees centigrade, the pressure would be around 78.33 millimeters of Hg absolute, and back pressure due to Cw flow, which has been calculated as Cw out temperature plus TTD, so that would be equal to the 49.79, and back pressure due to Cw flow, that would equal to 91.68 millimeter of Hg absolute, that is from steam tables. So we have calculated the back pressures due to these two both. Then we calculate the variations in condenser back pressure. So the variation due to Cw inlet temperature would be equal to the expected back pressure minus the back pressure due to Cw inlet temperature, which comes out to be around 20.604 millimeter of Hg. Then variation due to Cw flow, which will be equal to back pressure due to Cw flow minus the back pressure due to Cw temperature. That comes out to be around 13.35 millimeter of Hg. And the variation due to dirty tubes, which will be equal to the condenser actual pressure minus the back pressure due to flow, because of the flow. So that the variation comes out to be 29.12 millimeter of Hg. So the total variation would come out to be around 42.47 millimeter of Hg. So here we have calculated the variation due to Cw flow as well as variation due to dirty tubes. So this is important, that the variation due to dirty tubes is around 29.12 millimeter of Hg, or around 30 millimeters. So which can be corrected by means of the condenser tube cleaning. Or now we can have an Excel sheet designed for this particular exercise also. Herein we can calculate you can see the data has been there on the left hand side. You will see the data, and the right hand side you will have all the calculations. So you can have an Excel sheet prepared like this, and you can lastly the variation due to CW in temperature, the variation due to so here you can get whether the condenser tubes are means how much we are losing because of the dirty tubes, how much pressure we are losing because of the condenser dirty tubes. That can be calculated like this. So Excel sheet can be done and it can be found out. Now the this is another case wherein you have the design and the test parameters also. So herein you can see the load, condenser pressure, CW in out, condenser temperature, air suction temperature, and the calculated parameters are there on the saturation temperature, then expected back pressure, then again the design CW temperature rise, design TTD, and back pressure due to CW inlet. All these are calculated parameters. So you can see here the variation due to dirty tubes. In this case, it is coming out to be around 39.8 millimeter of Hg, and so because it is much more like 40 millimeters of Hg you are losing because of dirty tubes. So this can be. Now there is one more impact of condensate subcooling on heat rate. If you are subcooling the condensate, then there would be an impact on heat rate. That also can be calculated. So when condensate in hot well is cooled well below the saturation temperature corresponding to turbine exhaust pressure, the duty of the first feed water heater increases and thereby causes enhanced extraction stream flow. For an approximate 2.5 degrees subcooling, when throttle flow beginning with 30% is plotted against the percentage increase in turbine heat rate, there is around 0.001% increase in turbine heat rate for every subsequent 10% increase in flow. So this is the impact of condensate subcooling. This also can be taken into account, which may be a factor, considerable factor. So what should be your approach for analysis? This we have already discussed in our last video also, but here again I am going to quote about the condenser back pressure. If it is high, then the CW temperature may be higher than the design, or the if it is higher, CW temperature is higher, then your CT cooling tower is not cooling water, or there is some problem with the CT. Then if it is no, then if the temperature is correct, then the CW temperature rise is higher than design, then CW flow low or high heat load may be there. So it is yes or no, it is there, and the flow chart is also there. You can find out the what may be the problem. But the variations due to the CW, due to dirty tubes, that can be calculated, variation in the back pressure. So with this, thanks for watching. Please comment, like, share and subscribe Total Output Power Solutions. I take your leave. Manohar Tatwavadi. 93 mobile number is 93721671165.